Hi there, I'm Dr. Janet Cotton. I am the Managing Director of 180 Materials Testing, and today I'm going to explain our approach to root cause failure investigation. Why conduct a root cause failure investigation? Failure of engineering equipment, products and components generally costs somebody quite a lot of money. It may be associated with an insurance claim or a liability claim, or just the point that the product or the process has failed and throughput has slowed down for some reason. Who then needs a failure investigation? It's generally owners of assets such as ships and other vessels and other equipment and machinery. It will also be manufacturers of products who are producing, for example, beer or wine or cheese, and they have an equipment or machinery breakdown. And also fabricators who are manufacturing equipment and have a failure need to understand why the failure occurred to prevent further failures from occurring in the future. 180 has 19 years experience in root cause failure investigation. We investigate failures of all engineering equipment made from any engineering material. That includes all the metal alloys, ceramics, composites, polymers, and all industrial chemicals. So we provide a holistic and bespoke service in the field of root cause failure investigation. Our approach is also very unique. We use failure mode effect analysis to guide us through the process of root cause failure investigation, and we are very determined to always come down to the exact root cause, eliminating all other possibilities or combinations and permutations for the failure. So first of all, we start by having a look at the fracture surface. Here I have a little bolt that failed, and we will investigate this fracture surface with a light microscope or also a scanning electron microscope so that we can understand what type of failure has occurred. It could be a brittle failure, a ductile failure, or a fatigue failure. For example, I've got two studs over here that failed in unilateral bending fatigue, as opposed to this stud over here, which failed by fast brittle fracture. So once we understand what the fracture surface is telling us, we also have to analyze the material to understand what material has been used for the component, because this, together with the fracture surface, tells us quite a lot about how and why the failure occurred. Once we understand the mode of failure, we need to find the source of extraneous load, whether that is in fatigue or a high stress event. We have to find the source of that load on that component which resulted in the failure. And then it becomes important to consider the failed component in the global picture of where it functions. So for example, a big end bolt on a main engine is influenced by all of the components in the main engine: the pistons, the connecting rods, the bearings, the cylinder liners, etc. That is where we have to consider the failure in the broader context of where the component is operating. In the case of corrosion failures, we have to also then find the active elements that are driving the corrosion process. To do that, we take the sample with the corroded surface to the electron microscope, and we conduct EDS on the corrosion product to find the active elements that are driving corrosion. For example, chlorides drive corrosion and stress corrosion cracking in stainless steels, whereas sulfur drives corrosion in aluminium alloys and zinc alloys. So we put all of this together, and we also spend a lot of time on site, asking questions, interviewing various people, and this whole iterative process results in a very successful root cause failure investigation, where we are able to tell you exactly what the root cause was for the failure. And so 180 has built a reputation of reliability, integrity, and effectiveness. It's our goal to find the root cause so that future failures can be prevented.